Wonderful. Thanks, Django, for the introduction. Hi, everyone. I'm Pedram Johari. It's a pleasure to be in this class today. I'm a principal research scientist at the Institute for the Wireless Internet of Things at Northeastern University. And what I'm going to talk about today is one of the projects that was funded by the NTIA last year, and I'm the main PI of that project. And we are trying to enable digital twins for open radio access networks. Then I'm going to talk a little bit more details about what we have been doing in the past few years and what we are trying to achieve in this project. Feel free to stop me at any point of time if you have any questions. I will try to keep it brief, but also wide in terms of the perspective of a variety of different topics that we're working on. And towards the end, I will just open it up, for more questions, and we can, have a more deep dive into the topics that might be of interest to any of you. The work that I'm going to present today is a joint work with my colleagues and collaborators, including Professor Tommaso Melodia, Dr. Michele Polese, Dr. Salvatore Doro, Dr. Leonardo Bonatti, Dr. Gabriele Gemi, Davide Villa, Clifton Robinson, Mia Tehrani, Paolo Testolina, again, he also has a PhD, and Dr. Stefano Bosani. These are my collaborators, most of them research assistant professors and principal research scientists such as myself, and some of the professors, including a few students who have been helping us with this project. To start things off, I would like to introduce you guys to our testbed platform, Coliseum. Some of you might have already heard about this. Dr. Guan has his own team and access to the Coliseum network emulator. And if any of the students who are working with one of the faculty members within the United States, you are more than welcome to request the team and get access to Coliseum. What Coliseum is essentially, as of today, 25 or more racks of servers and radios. It's the world's largest wireless network emulator with hardware in the loop. When I say hardware in the loop, that means that we have software-defined radios. Those are provided by NI, the X310s. You might have some experience working with them in the lab environment. On Coliseum, we have 256 of them installed in the data center. And then they're connected, each of them, to a dedicated server to run the wireless protocol stack and then stream the IQ samples to the software-defined radio. And then we have a channel emulator called MChem that, as of today, it has 320 FPGAs that runs the channel emulation. And the way that it works is based on FIR filters, or finite impulse response. Everything happens in baseband in Coliseum. Nothing goes over the air, and that's why we call it a network emulator. But again, if you detach the MChem and attach antennas to the software-defined radios, essentially you can have an over-the-air communication, very similar to what you have on over-the-air testbeds. As of a couple of years ago, we have rebranded Coliseum to the Open RAN Digital Twin, because we have a complete full stack operational open radio access network performing as G-Node B and UEs on Coliseum. And this is accessible to all the users who are interested to do experimental research on the Open RAN activities. As you can see in this graph at the bottom of this slide, and hopefully you can see my pointer as well. Let me actually switch it. Okay. The blue boxes are a combination of 32 Dell computers. Each do have a USRP X310 software-defined radio. And we have 4 of these, what we call them quadrants. So in total, we have 128 of these nodes. Each of them do have 2 radio front ends that will give you 256 radios. And the channel emulator, which is marked as a green box down here, essentially has interconnection between all these 256 radios as the transceiver, and you can have the other 256 receiver nodes. So you can imagine a matrix of 256 by 256 channels, and that will give you up to 65,000 simultaneous RF channel emulation, with the bandwidth of each being 80 megahertz. So this is by far the largest wireless network emulator in the world. And as I mentioned, it's fully programmable, and we have protocol stacks for the Open RAN. In addition, we have GPUs that will help you with the applications of artificial intelligence and machine learning for any part or any components of the wireless networks. In particular, if you're interested again in open radio access networks, the notion of the RICs or RAN intelligent controllers is where you're going to use AI and machine learning. And again, we have created blueprints and ready to use containers that students and researchers can start from those containers that we provide to you, and then you can develop your own AI. You can collect data and you can train your machine learning, and you can explore and test and experiment on this network emulator. I just wanted to give a brief overview of the core facility that we use for enabling digital twins for wireless network experiments. And the rest of the slides that you will see today, you will see a lot of reference to this first slide. And when I say Colosseum, now you have a sense of what I mean when I say Colosseum. That's the data center that we have for wireless network emulations. This is an overview of different components of our digital twinning framework. Again, at its core, there's Colosseum. But there are different components that makes it a real-time digital twinning platform, and this is what we have been working on in the past few years. As of last year, the work has been funded by a grant from the Public Wireless Innovation Funds provided by NTIA. Myself, Michele Polessa, Salvatore Dura, and Tommaso Melodia are the co-PIs on that grant. And what we are trying to achieve is essentially in four separate but interconnected trusts. One of them is the blue box that you see up here, and that's what we call it the live twinning. I'm going to spend most of the time on this box in the talk that we have today, and then I will briefly touch on the other ones right now and later on some of the slides. On the white box, what we're trying to achieve is essentially the work has started from what we call it a tool chain that we call it CAST, and that's a tool set and pipeline that we have on Colosseum to create or digitize real worlds and create the digital twins. This is at the environment or physical layer. So you have, for example, in an outdoor environment, you have buildings, streets, and objects. And you have your UEs or user equipment that can be mobile, for example, in a V2X scenario, it could be cars and vehicles or pedestrians who have their own cell phones. And you can also have base stations at different buildings and whatnot. You can see that on the map that, for example, in Boston, there are 3 base stations, again, randomly distributed at different locations, and you can have UEs distributed in different areas. What happens is we digitize that, we create the 3D models, and based on that, we do some channel modeling, and I'm going to talk about the channel modeling later on. We have different ways of create those channel models, and then we'll feed that to Colosseum to emulate those channels or replicate what happens in real world. That's what we call the digital twin. In the work that we did 2-3 years ago in the CAST toolchain, CAST, and you can find the reference in our website. We also have a sounding component. What it does is essentially it runs a pseudo-random code in the digital twin. It creates the channel impulse responses, and it will compare that with what happens in the real world. Very similar to the standard channel sounding practice that people do over the air. But here we do it on the channel emulation system. So that will complete the loop of creating the digital twins and validating or testing them, making sure they are keeping the fidelity of the real world environment. What we are doing today, and I will show you towards the end of this presentation some recorded demos. As of today, we can create these digital environments in near real time. So depending on how you're creating your channel models, we can do that within a millisecond or up to 10 to 100 milliseconds. So we can create those world environments on the fly. You can go ahead and change the locations of the UEs and base stations in a GUI. It could be a simulated environment or in real world. And then that will be deployed in real time with all the mobility and whatnot in the digital twin, and then in that, what we call it a risk-free pre-deployment digital twin environment, you can do all the experimentations that you want. Think of it as a tool for mobile operators, for example, AT&T and Verizon. If they want to deploy a new feature, it's not really trivial and practical to deploy that on a real network and then have the users to test it, right? Because you don't know if everything will work in the way that you expect it to work. So what we have here, we can create that environment in our digital domain. We have shown that it preserves the fidelity of the real world. Now we have this real-time component. So everything that happens in the real world, I can replicate that in real time in my digital twin. Now I can add the new features only in my digital twin, test that, run some experiments. Of course, I have some thresholds to meet. If everything looks good, then I can deploy that back to the real world again at a click of a button. So that's the whole goal of this project. Again, the blue box is mostly focusing on ray tracing, creating channel models, and see how the wireless electromagnetic signals propagate in that environment, whether it be indoor and outdoor. The yellow box that you see at the left is creating a link between the two twins, the physical and the digital, or the real and the virtual one. This work will be presented, the yellow box, at GlobeCom this year. We call it TwinIt. That's again using MQTT protocols and whatnot to have a subscriber add the digital twin, and users can send that information to that digital twin. So this creates the networking and the link between the two counterparts in real world and in virtual world. And then the orange box on the top is our CI/CD/CT platform. That's continuous integration, deployment, and testing. Continuous integration, continuous deployment, continuous testing. And that's a pipeline that will take the latest and greatest versions of the protocol stack. Some Jenkins jobs will run on GitHub and GitLab repos, and then we have some Ansible jobs on top. It will create the protocol stack. It will download it on the software-defined radios that we have in Coliseum. It will run some default experiments. It will collect some KPI, and it will benchmark it against the previous versions of the code, and it will produce some artifacts and results of that experiment. And this happens in a continuous and automated fashion. So you don't have to do anything for that. As of today, 4 times a day, we take the latest version of the code, we containerize it, we put it on Coliseum, we also put it on our over-the-air testbed platforms. We run the test, we create the results, and we keep the log of it. So all the time, users completely transparently will have access to the open source code, and they know if that's functional and it's working, and they can also benchmark it against the previous versions of the code. So that's our continuous integration, deployment, and testing. And then the green box that you see down here is essentially providing access to the community to use all these features that I just explained. And that happens through a remote access using internet. So anywhere in the world, you can connect to the system. We have a portal for Coliseum. We are working on an extended or enhanced version of that portal for the DigiRound project that will give you access to the live twinning, to the networked tuning, and CI/CD/CT platform. We can also provide exclusive VPN access based on the need of some of the companies or users or researchers who do want to have access to exclusive devices. And as you see on the bottom right, you can also introduce your own device. As you saw in the previous slide, we provide all the servers and the radios, currently using software-defined radios. Currently, all of them are X310s. Those are the standard radio nodes that we offer, and you can definitely use them. But often than not, especially at the industry, they have their own RU unit, for example. If you're familiar with the vocabulary of Open RAN, it's a disaggregated network. You have a radio unit, you have a distributed unit, and you have a central unit. So that's RU, DU, and CU. And what we can do, essentially, you can bring your own components. For example, a company, let's call it Rakuten Symphony, they have their own DU. I can integrate that with my testbed platform, that's Coliseum. That's a feature that we call it bring your own device. And I can integrate that with Coliseum. And then you have access to all the other features that I just explained. So you can think of a vendor who is in the business of creating radio units, and they want to test that in the real world. but that's costly and expensive. So what they can do, I can create the digital version of that world for them. They will bring their own device, and that's a real device. We can connect it to our network emulator, and then I can run all those testing and produce that results in a virtual environment. And in multiple different publications that I can share the references later on, we have shown that we keep a high fidelity in terms of creating the results. So we have done this practice in real world, and we have done it in the digital twin, and we have shown that's almost perfect match with up to 95 to 98% accuracy, preserving all the KPIs. I'm gonna pause for a second, Jangyu here. Just want to connect my laptop to the charger before it dies. I just saw the notification. Just give me 1 second. Sure. Sorry for the short pause. So a little bit, more technical diving on what happens in Coliseum, and how we can integrate the Open RAN different components with this testbed platform. Again, at the bottom, I'm just repeating what you have already seen. Here I have the software-defined radios, the channel emulation system, the GPUs for the AI, the traffic generator component that will generate the traffic for you, and the infrastructure for management and access and whatnot. So now you know that you can get access to these testbed platforms. What happens is users can create virtual RF scenarios. For example, here you see Colosseum in Rome. That has the same name as this testbed platform. And as you can see, I have decided to, again, this is a virtual environment, right? I can play with the base stations and UEs in any way that I want. I have placed 4G Node Bs, and the red dots that you see are my UEs. And I have distributed them in a fashion around the Colosseum area. So that's the core components. That's your environment that you're building. Then on top of that, for each of these servers and the software-defined radios, I can program them with user equipments. In this example, for example, I have 6 UEs. Again, I'm virtually creating them. Depending on the application that they have, I can allocate slices for them in the network so that they can reserve the resources that they need, and then they can achieve the applications that they want. It could be video streaming, it could be just texting or voice. And then on some of these, again, similarly, the same server and the same software-defined radio, on some of them, I'll just program them as base stations. So again, each of the nodes that you see here, some of them are acting as base stations, the other are acting as UEs. Again, this is a programmable hardware, and you can program it to what you desire. Then on top of that, you will have the RAN intelligent controllers that runs on the GPUs. So I have the physical environment. I have emulated how the wireless signals are going to propagate. I have some mobility. Some of the nodes are moving to different locations. They are communicating to a base station. And then on top of that, I would like to develop some applications using AI. So I can collect all that KPI. I will just feed it to my, what we call it, the Open RAN near real-time RIC, or the XApps. And RIC stands for RAN Intelligent Controllers. And then here, through some interfaces and agents that I'm not going to get into the details, but if you're interested, of course, we can get into that in the Q&A part. I can go ahead and do different things. For example, I can do data collection. Then I can train some AI. Then I can deploy that AI. For example, one of the applications could be KPI monitoring, right? I can have an XApp that just looks at different data that's collected and then creates a visualization of how the KPI looks like. Or I can have an XApp to do network slicing for different, again, demands of the traffic from the different users, and I can deploy that on the base station. Again, this will give you a complete network or wireless network setup on an emulated environment. Once everything looks good to you, once you do all the tweaks that you want, once train your AI, come up with your topology of the network, even figuring out where is the best location for a base station if you are doing some network planning. Once you have that emulated environment set up in the way that you want, you can take that as instructions, and then you can deploy that in your real world. So that's one of the applications. The other application is you have a real world deployment, you replicate that exact same thing in the emulator, and then you change some of the parameters and see if you can improve it. If that happens, you can communicate back to your real world and then update that information. Hopefully that will clarify a little bit more of the goal of this project and the work that we are doing around the digital twin. I have a few slides that I'm gonna go through them very quickly because some of them are repetition of the general idea that I said. As I said at the very beginning, feel free to stop me if any of these slides has something in it that raise your curiosity and you have questions. Just stop me and I will just explain a little bit more. This one is talking about how we create the digital worlds. I already talked about CAST. It creates the digital scenarios and it will do the sounding or validation. I will end up having the real world and the digital world. We have done this practice indoor and also outdoor. As I mentioned earlier, the first work was called CAST. This is published in March 2023. Feel free to take a look at that work. There's a conference version that was presented in WinTech, and then in 2022. And then there's the journal version that's published in TMC in March 2023. Both of them are available on our website, and you can take a look at them. For this work, we used Wireless Insight, which is a commercial ray tracer. So we created a 3D model of our indoor environment. This is our lab in Boston, the ISEC building. We created a 3D model. And after that, we run ray tracing software. We create the channel models and we'll feed it to the MCAM. This is another example. This is outdoor. This is a collaboration that we did with the Department of Transportation. This was a vehicular communication example, or V2X. And then what we did here, we had a couple of vehicles and a base station, and we had some mobility on that specific road. And this was actually something that they experimentally did in real world. So they had these radios and they did this exact same process in the real world. They provided the information to us and we created a digital twin for them. The benefit of that was, the repeatability of the digital twin, and we started to collect more data. And on top of that, we also developed some features and we did some testing, and then we brought it back to the real world. The process of creating that, this is a framework that we have on Colosseum today. So the new researchers can come up with their own scenarios. You identify a location anywhere in the world, outdoor, indoor. If it's outdoor, we can update the 3D model from OSM. That's free and open source. We load it in MATLAB or Wireless Insight. We run the ray tracing function. You send us the set of nodes and the trajectory or the mobility of them. We run the ray tracing, we sample the channel, we parse the output. Then there is a quantization and approximation for the channels because Colosseum only understands up to 4 taps. I can elaborate on that if there's an interest, but eventually it will end up being an FIR filter, and I will install on Colosseum. Once this is installed, I will give you an ID for that scenario, and then you can run that on demand. Guess pretty much I covered this. This is a nice visualization of what we had for that CV2X project. I had a couple of OBUs on vehicles. I defined the nodes and the trajectory. I did the ray tracing. I parsed the data. I did the approximation and installed on Colosseum. Remember when I showed you CAST, it had 2 arrows. One was digitization of the real world and creating the digital twin. The other one was sounding or validation. This is the normal practice of channel sounding. So I send a pseudo-random code sequence, then I receive it on the other side. Everything is happening on my digital twin and not in real world. And then I do the correlation of what I receive after passing through that channel with what I sent in terms of the pseudo-random code. and then I will find the peaks, and that should be my CIR. And what I do essentially, I will just compare that with what the real world generates. The goal was to show the fidelity of the system. The goal was to show if my digital twinning platform is preserving what happens in real world. And can I rely on that? Can I go to an operator and tell them, hey, if you want to do this experiment in real world, this is going to cost you millions of dollars, but you can do it on digital twin with a fraction of that cost. The first question will be, okay, so you're telling me you have a digital twin, but how accurate are you representing the real world? So this is what we did to show the fidelity of the system and making sure that we keep the integrity of emulating those channels. Again, back to that same scenario in the collaboration with Department of Transportation a few years ago, what we have shown that what you feed and what you collect from the real world versus what you can do on the digital twin is almost the perfect match. Again, what you see on the left side is the CIR, the channel impulse response after the quantization and approximation. I only have 4 taps for every slice. On this axis, every 1 millisecond, I just call it a slice, I can update the CIR, and that's how I can have a mobile scenario. On this axis, this is my FIR filter, so this is in microseconds. On each of the slices, I can have up to 4 taps, and this is the time. As we go on, for example, here I have 200 seconds. This is, let's say, roughly 4 minutes, 3 to 4 minutes, right? Of course, this is replicating this exact same scenario. It takes 3 to 4 minutes for these vehicles to go all the way down to this end of this cross section and coming back at a constant speed. So that's why you see a V shape here, because they're going at a constant speed. And of course, the propagation delay will increase as I get further and further apart from the base station, right? And then here is what happens in Colosseum. Of course, everything here is continuous versus what you see here, which is discrete, but you can see that the pattern is exactly the same as what I have fed the digital twin with. This is a 2D cut of that graph, which will give you a better visualization of what happens. Again, this is my line of sight that you can see very easily here. And then the other tabs, the single ones that you see, are the multipath components are the reflections that I get from different buildings, right? And you can see that in my emulation, I'm exactly replicating that same thing, and even with the multipath components that are very accurately being emulated. And this is another cut. Here you see a U shape because I'm looking at the path gain or the path loss. As I'm sure that the path loss. When you report it in dB, it has an exponential relation with the distance from the source of your wireless signal. So that will give you like a U shape when I get further and further apart from that base station, and then again I will go back closer to that station. Starts from -60 dB, goes all the way down to around -100, and comes back. Here is the original taps, and again, this is what happens in Colosseum. And again, you can see I can preserve the accuracy of my real world. Very quick here, this is the orange box in the first slide that I showed. This is the CI/CD platform. I'm not going to go through the details. I'm sure at this point you get the idea. It's just pulling the new information. It's all software-defined radios, so I have to look at the protocol stack. I will take the new version. I will implement it. I will create a container. I will implement it on my software-defined radios. I'll do some testing, and it will keep a log of everything. Again, this has been supported partially by NSF, Department of Transportation, and Office of Undersecretary of Defense, OUSD, the RNE department. That's another project that we have running. It's called Open 6G, and this component was done and essentially was enabled through that grant. Another quick example is the indoor environment. This is our arena testbed. Similar stuff as what I showed in the external environment, the CV2X example, but this was just inside the lab and indoor environment. Same practice, same concept, different application. Arena is the over-the-air testbed. Coliseum is the digital twin. And as you can see, it follows the exact same pattern in terms of the throughput. As the time goes on, I've been moving one of the mobile UEs from one side of the lab to the other one, and some of the antenna arrays that we have installed in that environment has been acting as base stations to provide service to that UE. Another application that we just tried was a Wi-Fi jamming experiment. So I had Wi-Fi going on, I had a Wi-Fi transmitter and receiver on 2 nodes, and I had a jammer, and I was turning on and off that jammer with a narrowband jamming scenario and also wideband. And again, the blue and the orange is essentially showing you the throughput and the SINR. And the different markers that you see here is telling you whether it's running on Arena or Coliseum. Again, the same pattern for the throughput and also the SINR on both experiments is what we observed. And that tells you that the digital twin is preserving the fidelity of the system. Again, this is just another example that we did for CBRS with incumbent radios. Essentially, it was a satellite communication, and then we had a 5G deployed network. The location that we chose was in Hawaii. Same practice. I had mobile nodes, and wherever I detected a radar signal, which is the incumbent radio, I could send a signal to my 5G deployed network and stop transmitting to prevent any unintentional interference on the radar or the incumbent services. As you know, with the spectrum sharing and the coexistence of different technologies using the same spectrum, one of the things that you got to make sure is to make sure that you're not causing interference above a threshold to the incumbent radios. And that was the goal of this practice. Again, we did that on our emulated environment, and we have shown that in real world you can deploy the same structure. This work was presented in WinTech again in 2023. That was in Madrid, and the work was led by one of our PhD students, David Avila, and another student, Daniel Uvaidov, who actually used to be one of my master's students in University at Buffalo, like you guys, a few years ago. Then he joined Northeastern, he finished his PhD, and right now he works at Qualcomm. This is exactly what I just explained. You have some 5G activities here. Then I detect some radar transmission at the same frequency and the same band. I will send a signal to my 5G network to turn everything off. You can see there's no 5G activities during this time. As soon as the radar activities are done, after a few seconds, I can turn on automatically my 5G signals. And this is just a visualization of what happens in terms of the movement of that Navy ship that's using radar. I'm gonna skip a few slides here to get to a demo that I wanted to show you you guys in the interest of time, and I will open it up for questions so that we have a little bit more time if there's any interest on any of the topics. But real quick, this is another work that we did similar to what I explained. This is called Boston Twin. Rather than just focusing on a small location indoor in our lab or a small location outdoor, for example, the Tampa, Florida CV2X scenario that I showed, this is what we did for the entire Boston city. This work is also published and also featured in NVIDIA website because it used Siona for the ray tracing part. Siona is another tool that you can use for both wireless simulation and also ray tracing. And we have a complete digital twin version of Boston Twin and at the physical layer. And of course, we can deploy components of it or piece by piece on Coliseum Network Emulator. I'm going to skip the slides. This is the reference if you want to take a screenshot, or this is being recorded. I'm sure that Zhangyu will share the slides with you guys afterwards. Feel free to take a look at this paper. And if you have questions or if you want to reach out, let us know. This was presented at the ACM Multimedia System Conference in Bari, Italy, I think it was back in March of 2024. Again, same idea. This is Boston, and we have shown, again, simply we just put the Shannon capacity to show what areas can receive more than 30 megabits per second of service and what areas can receive more than 700 megabits per second. And for the base station distribution, we use the OpenCell ID. So this is actually the real deployed base stations in Boston environment. Another piece of work that I will, again, go through the slides very quickly is a collaboration that we did with Viavi Solution. That's one of the industry partners of the Institute for Wireless Internet of Things at Northeastern University. Here we are actually using AI and machine learning to create heat maps or the path loss map of areas. When you do ray tracing, it can take up to hours and days, depending on the area that you do the ray tracing. But now we have an AI tool that we can do it in the matter of tens of milliseconds. So we accelerate the speed of creating those heat maps so that we can have the real-time digital twinning feature. I think I do have a little video that I will show you about in the next slide about this topic. But this is a good summary. So it takes hours to do a small area. I think this one is 500 by 500 meters, Northeastern campus, creating a heat map of the system of that environment using high fidelity ray tracing with the Wireless Insight, which is a commercial ray tracer tool provided by Remcom. That's the company who creates that tool. They also have a fast RT function. It can do things a lot faster. So if you do the high fidelity, it will take up to hours. If you do fast, it will be milliseconds. But as you can see, we'll lose all the details, especially when you go to non-line of sight areas. And it can be up to 20 dB on average error, which is quite high. But with our AI model, we can do it in 30 milliseconds. And as you can see, it preserves all those details. And our error is only about 5 dB and sometimes even lower than that. And we run that on GPUs. Yeah, this is a video. Let me actually see if I can play the video.
Let's drive you out.
So what is happening here, I have Boston area campus and I have distributed possible locations for base stations. And I will go ahead and click on any of them. It will generate a 500 by 500 meter square. Recorded results from Wireless Insight takes up to an hour to generate that. The fast ray tracing using Wireless Insight will be in 30 milliseconds, but the error is pretty high. And what we do using GPUs, we only add 17, 15 milliseconds on top of that, but we reduce the error all the way down to sometimes even lower than 2 dBs, or on average, I think 3 to 4 dB. We can run it on CPUs. Of course, it takes a little longer, up to hundreds of milliseconds. Again, preserving the exact same, because this is the same algorithm that's running. It's just the difference is running it on GPU versus CPU, and preserving that error. I think I only have one more video that I wanted to show you guys, and then I will just open it up for questions. Yep, this one. So this is another demo that we have. This is not on our production environment yet. This is in our sandbox or pre-prod that we are developing today. But what you can see on the right-hand side, I have a GUI with, again, a simple scenario, one base station, and 3 UEs. And again, I just randomly, chose a place in Spain, but you can choose anywhere in the world. And what I do, I can drag and drop these UEs. Behind the scenes, I have the 3D building map of this area. Within 1 millisecond, this is the refresh rate. Every 1 millisecond, I figure out if there's line of sight or none of sight. Then I will take a stochastical channel model. I will calculate the path loss. I will feed that to that data center that I showed you in the first slide, the data center with 25 racks of computers and radios in the loop. I will emulate that scenario on Coliseum. And on top of that, I put Open RAM protocol stack, and then I collect some KPI. Again, think of it as, again, this is your playground. You're just playing in live with all these components, and I will feed that in real time to actual radios. I emulate that environment and I collect some measurements. Very simple example, but you can imagine that once I have this KPI, of course, I can, on top of that, I can, start developing some machine learning algorithms and add some intelligence and then deploy that back to the network. I'm going to play this one more time so that, you can relate to what's happening. You can see the nodes are at different locations. I will collect all of them at one location. And of course, what I expect is the, RSRP or the received signal strength is going to be almost the same for all of them. And that what happens, when I bring that red node, you will see that will also drops down to minus 67 dB. And then similarly, I'm not changing the MCS, but you can see the throughput in downlink and uplink will go up and down as I'm moving, and I'm not feeding that much traffic. This is just the basic, broadcast channels that I'm using right now. One of the key components that you can see is essentially the RSRP. As I get that closer to the base station, this will go up. And as you could see, I could also move the base station, and that's another cell planning tool. That operators could be quite interested in that. So you can move the base station and try to find or optimize the best location to put that antenna. Again, here I'm doing it by hand just as a demonstration, but this can be automated to find the optimal location in a loop and then spit out the results without the visualization. I think I'm gonna stop here. Because we already spent around 45 minutes. I have a few more slides, but I will just stop here and I will open it up for questions if there are any.